Okay, cool. It's being recorded. All right. So, oh wait, that's not the right screen. There we go. Okay. So I got 4 problems that I'm thinking about doing. It's just one from every subchapter of y'all's thingamabobber. Am I in this? Oh, there we go. There we go. Wait, nope. Okay. Yep. Okay, my mic is good. Okay. It's just one from every like subtopic in y'all's problem sets. So 4 problems. I'm gonna start with complex power. So I feel like at least the census that I was given, or kind of from just talking to people, it sounded like the last problem on y'all's last problem set, the complex power, the one with the wind turbine thing, was the most difficult complex power one. I'm not saying it was extremely difficult, but it was probably the most difficult out of those 4. Would y'all agree? Or yes? Okay. So this is a problem from my test last year. And it's basically the dual of the problem y'all have. That's what it is. So I'll read it. The network shown in Figure 3 represents the connection of a single-phase wind turbine driving an active load. The Norton's equivalent for the generator is shown in the wind turbine box. The time domain expression for the generator current source is j omega t of time equals 500 milliamps cosine 4t. So yeah, the RLC network connected to A and B. To the right of the turbine is a model of a known active load in the network with 0 initial conditions. You are asked to calculate the values for the following: complex power. It's just S. Is it just S? Right. That's what he calls it, right? Okay, cool. In volt amperes, average power in watts, and reactive power in vars, and the power factor, PF. And the type, value, and connection at terminals A and B of the component that will correct the power factor to unity. Show all the work, explain whatever. Okay. So we're given a current. What does that current tell us? It is a it's a time fluctuating current, you'd say, right? We're given. Put that in a phasor domain. What is it? Exactly. Now, what does the 4t represent, or what does the 4 and the 4t represent? Yep. So j omega t phasor equals 500 milliamps, and omega equals 4 rads per second. Do you agree? All right, cool. I'm going to move this over here. So, okay, yeah, that works. All right, so on y'all's problem set, you did the evidence, which was name. Now we're doing Norton's, which is what? Name, exactly. So what do you think we do first? Would you say impedance, or since we're using name? Yeah, there you go. So name, well, with the Norton's equivalence, you always do like a, what do you call it? Arbitrary current source. Am I right on that? So let's just go ahead, not current source, I'm sorry, voltage source. What am I saying? So let's just go ahead and just kind of make this VAB an arbitrary voltage source, and I'm just going to call it EG of T. That's a really bad T, but y'all get what I mean, correct? Any questions? All right, cool. So, well, I'm going to keep the same polarity, which that's plus, and that's minus. Keep the same polarity. So, doing the main, right? I am 1. I am 2. All right. Does anybody got a photo? Do y'all want to take a photo of this real quick before I do stuff? Still good? Okay, bet. All right. So now we just do the name. So mesh 1, I mean, not name, main. Mesh 1, we have, what do you call it? R1. And I'm going to do, it's main, so it's impedances. So 1 over SC2. What's being shared between the two is just 1 over SC2. Same here. And then we have 1 over SC2 plus SL3. I am 1. I am 2 equals. We got EG of T. That's an I. EG of T. And is RMI2 of T, is that negative or positive? With the way my arrow is oriented. Negative? Do we agree? What if in this thing here, will the R2 or RM I of 2, would that be negative or positive based on the orientation of my arrow and the polarity of that source? I agree with that, but I'm not just going to matrices. So this one here, someone said it, just negative RM I2 of T. But I agree with you there. We'll get there here shortly. So I2 of T, no, it's all good. I2 of T based on this and the polarity of my arrows is what? I agree. So that will be, if I put this down here, EG of T, 0, separating into the two sources, 0, 0, negative for that, or negative for RM, and there's a negative IM1, so that'll just be RM for the first one, and then it's negative RM and a positive IM2, so that becomes just negative RM, multiplied all by IM1, IM2, just like Phoenix said. We agree? Okay, cool. So then we will simply add the, or subtract those over. R1 minus 1 over S, didn't look good. 1 over SC2, negative 1 over SC2. And then I'll have negative 1 over C2 minus RM when I subtract. What's up?
Your independent source?
Yeah.
Is that? Yeah. That's what
I got you. That is EG of T. Just like the last one. You got any questions? Just say it. Just say it. Well, we're still in time domain. Well, no, I agree with Phoenix. That's supposed to be an S. That's supposed to be an S. You know, we're going to do the same thing here. Bloop, bloop, bloop. All right. I was just testing, you know, right? Okay, then this one will have 1 over SC2 plus SL3. Thank you. And then plus RM. Yes. So for this one here, it's a positive, but we subtracted it over, so then it becomes. No. So this IM1 here is negative, but it'll be multiplied by a negative RM2. So for and then the opposite for IM2. So then we got that there, and then this is IM1, IM2 equals EG of S. All right. For the sorry. You're right. I don't know why I put a minus there. Might be. Right here. There was a minus here. So, man, I'm so happy I found that laser tool. It's so freaking handy. All right. For those who just came in, that's what I got going. If you want to take a photo of that, no problemo. It'll be on the recording as well, and the HKN teams. The problems are yes. Well, I can post my work there too later. Okay, so now that we're at this step, okay, what do you call it? Just for power stuff, you want to be in the time domain. So, well, I shouldn't say time domain. You want to be in the frequency domain. So what should I do to change to the frequency domain if we're in the S domain? Okay, well, Laplace is S domain, but how do we get to the frequency domain just from Laplace? Because S equals JW. That's what I was looking for. So S equals JW. Then these will just become, now this, I think that's what I put the minus because I was just skipping ahead a little bit. So this will just become R1 minus J over omega C2. C2, then this will just become J over omega C2. This will then become J over omega C2 minus RM. And this will become J omega L3 plus RM minus J over omega C2. And this is all just still equal to, that's supposed to be a 1, IM2 equals EG, that's a horribly, EG of J omega 0. So the reason that is because this is just 1 over J omega, which is the same as saying negative J over omega C2. all agree with that? So that's why these then become negative when the J is moved up top. So when putting in those values with a capacitor value of 50 millifarads, resistor of just 10 ohms, and an inductor of 1 Henry, we have these values. Do y'all want me to do the, like, y'all cool if I just skip ahead and put the values in? Y'all cool with that? Okay, cool. We will have 10 minus J5, those are 5s, J5 minus 2, and then 2 minus J. Okay. And then IM1, IM2 equals 2 EG of T. Remember, it's just a, what do you call it? It is just arbitrary. That's what I'm looking for. Okay, so like we said earlier, we want to find the admittance. So the reason why we will find the admittance is we have these here, okay? When you add these two together in admittances, it's just simply like adding two resistors or two resistors in series. That just makes it easy on that. And then we want to find the admittance here so that just current division and just math in general will be relatively easier. Does that kind of make sense? Does anybody have any other questions on that? No? Yes? Okay, cool. So we'll do that. Okay. So the YAB, right? Okay. Well, YAB is just simply, the inverse of impedance. So instead of being voltage over current, it's current over voltage. So we'll just call this IAB over VAB. Okay. Well, VAB, we've simply just have that source there, that EG of T, but now it's EG of a J omega because we're in the J omega plane. So that can then just be changed to EG of, I'll just put J omega, and the IAB. Okay. Well, looking back on the matrix, what would IAB be in terms of matrix currents? Did that question make any sense? It didn't make sense? Okay. What is EG of T in terms, I'm sorry, not EG, sorry. What is IAB? So like the current that would be here, what is it in terms of these matrix currents? IM1. Do we agree? Any other questions on that? Cool. Well, I agree with that. IM1. So this then just becomes IM1, we'll just keep the phasor, why not, over EG of J omega. Okay, well, what is IM1 in terms of our matrix? I almost agree with that. Delta 1 over delta, yep, EG, I'm going to call it J omega. So when you plug that back in, that's not supposed to be an A. Oh my God. YAB equals delta 1 over delta. These are bad deltas. EG of J omega all over EG of J omega. Those cancel out. And YAB those equals delta 1 over delta. Okay. Well, what is delta 1? How do you determine what delta 1 is? Okay, I agree. But what's the steps of that? Exactly. So boom, boom, determinant of whatever is left. This is nice, so it's a 2x2 matrix. That's the only thing left. We happy with that? Bet. So then that just becomes 2 over J. Okay? And then delta, as in a determinant, would simply just be this times this minus that times that. Did that make sense? Cool. So then you just 10 minus J5 times 2 minus J minus J5 multiplied by J5 minus 2. So YAB, doing the math, becomes 52.941 minus J11.765 millisiemens. Okay. Well, okay. So we have the, what do you call it? We have the, not impedance, admittance here. Okay. And we have, what do you call it? We have values here. So we have admittance in one side. We should probably get admittance in the other just to make it simpler. So we're going to do the admittance of here, which is simply just G omega T, or I shouldn't say omega, WT because it's wind turbine, plus the impedance of that capacitor. So I'll just make a new variable called YWT equals G omega T plus SC omega T. Do we agree? Cool. Which that simply just equals 20 plus J 20 millisiemens. Okay. Well, so like I was talking about earlier, current division. Current division will be our friend here. We have a current source here. We have admittances here, but we don't know the current or the voltage there. If we have a current source and we have admittances, we can then do what to find the current here? Current division? Did that make sense? Do I need to rephrase that? You good? Okay. So what I'm going to just call IAB is simply the admittance of what? Oh my gosh, I keep doing that. Admittance at that terminal AB all over the total impedance. Admittance, I keep friggin' saying that. At the whole thing, all multiplied by J omega T. We agree? Cool. So then we just substitute the values. 52.941 minus J 11.765 times 10 to the negative third. I'm going to rewrite that better. Times 10 to the negative third, all multiplied by 0.5 plus 10. Nope, that's not supposed to be plus 10. That's supposed to be plus J0. And the reason of that 0.5 is because given our phasor current is 500 milliamps, which is the same as 0.5 amps. So, am I going a little too fast? My bad. All right. But do we agree with, let me scoot this over. Let me scoot that on over. Do we agree with this multiple thing? What's being multiplied over here? Because of this J omega here, nope, JW of T, JWT, whatever. Because that's there, we then have to multiply the whole numerator by that, which the numerator, like we just saw, is just simply 0.5. I'm not even going to write the J0 thing. And then, as we did earlier, this is this, and this is this. Does that make sense? So we just plug those numbers in. 20 plus J 20 times 10 to the negative third plus 52.941 minus J 11.765 times 10. Yeah, times 10 to the negative third. All right. I'll give you all a second to write that down. We almost look good. Everybody got it? Cool. So plugging that into the calculator, you get this. YAB equals 34.93. Nope. What in the world? Okay, sure. 0.93. We'll do 5. Why not? Minus J 120.087 milliamps. I'm gonna double check something real quick. I wrote something wrong. What's up?
Just to make sure if I could read your handwriting correctly.
It's all good.
The polar form of YAB.
Yes.
Does that say 52.04 minus J 11.765?
52.941 minus J 11.765.
Okay.
You're good. I'm not gonna lie, I didn't really hear exactly what you said, so I just thought I might read it out. I got the free version. It's going to pop up again. All right, we're chilling. We're chilling. Okay, cool. So we have current, we have voltage. Do V equals IR. In this case, V equals 1 over G to find voltage. All right. So the voltage at AB equals IAB over YAB. That's a Y, a really bad one. Do we agree? Cool. So we take that number we just found. 34.935 minus J 120.087. We'll multiply it by 10 to the negative third. All over that minutes we found earlier of 52.941 minus J 11.765 all times 10 to the negative third. So technically, we didn't have to say that. Okay, VAB comes out to 6.769 minus J 0.764. And that's all volts. Okay, so the reason we're doing that, right, is because the first part of the question simply asks, connected to the nodes A, B, we're asked to calculate the following values. So now that we have voltage, current, and admittance there, we can find all of these things. Do y'all agree? Okay. So I know there are multiple ways to find S, but my favorite is simply just phasor form of S equals the voltage VA, voltage at the nodes AB times the complex conjugate of the current at AB all over 2. Has never failed me. I love it. Works. So those values simply just become 6.769 minus J 0.764 times 34.935 plus J 120.087 times 10 to the negative 3. It's all over 2. So SAB gives us a value, I should just say S gives us a value of 1.228 plus J 0.273. And what's that in? What is S? Yep, volt amperes. So that has 2 parts, right? What are those 2 parts? Real and imaginary, but that also tells us things we want to know already. Well, what does that tell us? So you said Q and average power. That's actually what I'm looking for. So average power is simply just the real part of S, and Q is simply the imaginary part of S. That's it. That means that power average equals 1.228, and that is in what? Yes, indeed. And Q is equal to 0.273, and that is in what? I agree. That's an R. That's really bad. Okay. The final thing for part A. I can. Sorry. Gotcha. That one? 6.769 minus J 0.764. No problemo. All right. So the last thing we have to do is power factor. Yeah, that's what it's called. Okay. So there's also a lot of stuff. As Richard was saying, we could find phase angle. I don't like to do that personally because I kept all of my stuff in rectangular, so that just would add an extra step for me. So what I like to do is, and this works just fine, it's the power average over the magnitude of S. That's it. So that equals to 1.228 all over the square root of 1.228 squared plus 0.273 squared. Our power factor becomes, get it right there? Oh, I did, cool, 0.976. And I believe that's unitless. Unitless, right? Cool. Okay, so the next part. Okay, I guess I'll put everything in. Do y'all want me to go back to any parts that I've done right now? Any questions on what I've done? Technically, yes. Yes. If you were to do things with angles, you'd want to do degrees for sure.
I think that's just if you want to do it. No.
I could have. Okay. The reason I said that, just yes to begin with, I could have sworn that's something Russell said to just keep stuff in degrees. Like I said, I don't fully know because I did this method more, so I never kept it. I never did anything with angles. I didn't want to. Like I said, it gets confusing if we need to do degrees or radians. That's why I just did this. But I want to say if I ever did stuff with angle, as in when we first started teaching it, it wasn't degrees. I want to say that's what we did.
He does do it in degrees, but I mean, I've always done it with radians, and I've never had any issues.
Okay.
He doesn't really understand radians.
Wait, really? Yeah, wow. Okay. Where's my backpack? There's my backpack. If it works, it works. But yeah. So if y'all want to do that, go ahead and do that. So now the next part is to it says the type, value, and connections at terminal AB of the component that will correct the power factor to unity. Okay. I'm not gonna lie, this is the part that I was the weakest on. I was talking to people, and it depends on the sign of your susceptance, I believe, of what component you will then use. Okay. So YAB, as we did earlier, right? It's got two parts. It's got a real and imaginary. But if you break that down into other things, that equals your admittance. No, not your admittance. Your conductance. I'm sorry. At terminals AB minus your susceptance at terminals AB. Do we agree with that? Okay. Yeah. Sorry. That's not much better, but it's there. We agree with that? So since it's a imaginary part, right? Negative J susceptance equals 1 over J omega, what do you call it? LAB. So if you put that on top, negative J omega LAB, negative J's cancel out, and you just get that beta, not beta, susceptance equals 1 over omega LAB. So that kind of tells why I did that is because give me one second. This is the admittance of an inductor. Do you agree with that? Okay. So we have a negative J over here, and when you put the J's on top, we have this here. So to cancel out the negative J's, you need this. If this was positive, if it was a positive susceptance, right? You can then just use J omega CAB because we need to cancel out the imaginary parts to then find what component is there. So if it was positive, I believe just use this. But since we have a negative, we needed to cancel out the two negatives. So that's why we did this. Did that kind of make sense?
Yeah.
Okay. On y'all's homework, has he given y'all solutions?
Yes.
Did y'all look at this problem on your homework?
It was weird. Every single problem was like something different.
Well, so I came into this issue last semester, sorry. And I was talking with a couple other people. I believe we came to the conclusion that Russell did his math wrong on problem 4. It just he did things where in the that's not what I want. On these terms here, he didn't put a negative on it, right? Because I looked at that and I remember I was trying to help a couple people doing that problem. And I looked at the solutions and I looked at their problem and I was like, those two terms are wrong, or these two terms are wrong. And they were like, well, no, it's not. And I said, well, I have different values. And they were like, well, this is why it's not wrong, or this is why they were not wrong. And I kind of agreed with him because Russell just had either an extra negative or not enough negatives terms there. Because I think it was like the terms were, I think like a negative J over something, negative J over something. Then you multiply. I think this one became a positive at the end. And there was a whole big thing. But basically, Russell's solutions in that instance were wrong because of those two numbers there. So on his solutions, he got a inductor. But I believe the correct thing to do is getting a capacitor, because on the correct values, this is what it would have been. Does that make sense? Or did I just confuse everybody? Hey, by the silence, I feel like I confused everybody. Yep. So basically, just go with this. If it's negative, do this. If it's positive, do that. Do we agree? But this is for this part. This part. And if it was flipped to where you had Z, right? Let's say you had a negative Z, AB. Nope, not Z. It'd be X because it's imaginary. So that would equal negative J over omega CA. Do you agree with that? Because this is the same as saying 1 over J omega CA. Let me write this all in a concise area. I think that'd be better. Negative J, that is the same as negative J over omega LAB. Positive J susceptance equals J omega CAB. And if we had a negative J XAB, that's the same as saying, that's supposed to be a negative, negative J omega CAB. And then if you had a J XAB, that's the same as saying this. Does that make more sense? I guess writing it concisely is probably a good idea. I'm going to let people write that down. All right. I low-key hate this part of the problem. The other part I thought wasn't too bad, but this one I kind of hate. I mean, I feel like y'all did a similar thing in EMAG too. Like it's like a similar formula.
I don't know, for me it was confusing the way he did it, because I took a look at the solutions after he posted it. Like on some, he already gave you like
a component
correcting capacitor, and he was like, turn this off, like pretend it's off first, then turn it on. And then for some, he's calculated at the end the equivalent load, like if it's inductive or conductive. Mm-hmm. Inductive or capacitive, yeah.
I got you.
And then the next step from that, he was like, okay, now if it was a capacitive load, he put inductor in series, and then the inverse for the other one. But then he didn't do that for the previous one. So I was trying to see what the difference was there.
I see what you're saying in terms of. Are you saying like the first problem you did for power factor? I have it pulled up on my laptop. Yeah, because he gives you.
He had one like in dashed lines, like a capacitor already there.
Yep.
That was straightforward, but like this one, I think for this one is the one where he found like, or he doesn't give you that component first. He
wants you to find it
like
like
he found the equivalent load if it was inductive or capacitive, and then he corrected it with something else. I don't know.
Yes.
You know what I'm talking about.
I know exactly what you're talking about. Yeah, I'm gonna get there here shortly. So since we have that negative susceptance, like I was talking about, this right. So it came to this. We are basically saying that it's going to be an inductive load because we have this here. Okay, we have a negative susceptance, and that is equal to a negative J over omega LAB. So we cancel out the negatives. So your susceptance is simply equal to 1 over omega LAB. So this determines that it's going to be an inductive load because we have omega and we have susceptance. So we simply swap that out, and basically through these things here, right? Since we have a negative J susceptance we were basically saying that it's going to be an inductive load. Does that kind of explain where that was going?
Yeah, I understand that, but more of my question was more towards like that part, that difference whenever he calculates that part first and then finds the power factor correcting versus whenever he already gives you that component and then all he did was I forgot what he used, but I think it was just a relationship to turn it susceptance into the capacitive value.
I mean, he might have used this. He might have used something like that.
Maybe. I'll just keep on with the problem now.
Gotcha. Cool. So then the inductive load will just become 1 over, we found our omega value earlier to be 4. And then susceptance, we found to be this 11.765 times 10 to the negative third. Did I write that? Yep. Cool. So then we put that there. 4 times 11.765 times 10 to the negative third. That'll get you of 21.25 Henry. Okay, I need to do something real quick. I need to add a page. Insert a page. There we go. Okay, cool. All right. So we're there. Okay. So okay. So this is how he draws it, which I get. I think this might clear it up or it might confuse you more. I don't know. As an inductor, this is terminal AB. We found that we have, a conductance and susceptance, and we've turned that susceptance into an inductive load. So we're basically saying this inductor here is going to be our LAB. We still have that conductance, GAB. Okay. Well, okay. So I think simply to counteract, what's up? Okay, good. Gotcha. To counteract that inductor, you have to put a capacitor. I believe that's the difference. So we'll have this capacitor of the power factor correction. Okay. And give me just a second. Yep. So then we have that admittance of AB. That's a horrible one. There we go. And that's basically at the terminal AB. And this, so at the terminal AB, we have the YAB. But if you separate that out, you have the conductance, and then you have the inductance. Sorry, because we had the negative susceptance. Did that clear anything up?
I guess what I did notice is that in his solution, he always did input impedance for every problem. And at the end, he would convert it to
admittance. I think it's because he wants to use just these top things here. He just wants to use these. Because technically, I mean, wait, no, what is it? That's supposed to be now. I don't see why this wouldn't work. But
he did use these. I guess my confusion at the end was that he always used input impedance for everything.
Mm-hmm.
So I guess that's what made a difference at the end, where
he swapped.
What you did here from the very beginning, you were like, you defined, okay, we're going to use admittances for this because of this.
I got you.
He never did that in solutions. He just did input impedance, and at the end, I guess he thought about it. Okay, yeah. So now, in order to get what we really need to get, we have to turn this into minutes, right?
I got you.
That's where the confusion.
I think it's just going back to this. So let's see. It's basically all just because we want to using MAME, you can find the admittance before that matrix or before that network by using MAME. For name, on the last one, it was name, you were able to find your impedance because it was simply you had ZAB, right? You had this would have been ZAB, and this would have been the voltage voltage at AB over the current AB. And since we had since it was name, it would have been that the nodal voltage equals delta 1, 1 over delta times the current. And the current, so that's kind of using MAME. It's easier to find the adminance of the network. And if it was MAME, I'm sorry, MAME will help you find adminance. NAME will help you find impedance. Did that kind of make sense?
Yeah.
I'll write that down. I think that's probably a better way to write that down. MAME helps find admittance. NAME helps find impedance. And do y'all understand why that's the case? I kind of just realized it now. But do y'all understand why that's the case in terms of like the actual math? Yeah. Do y'all understand that, or do you want me to explain it?
The source.
Source?
That's where you find current name divided by the voltage, which gets rid of the source.
Yeah. Yeah. And if it was the opposite, where we had a current source, you divide it by the voltage source to get rid of the other thing.
I guess if you don't want to explain from the beginning, because I feel like, I guess my confusion was figuring out whether to use the admittance part or the impedance part. So what in the problem told us, okay, we need to use admittances here, because if I know that, I mean, the rest is straightforward, and I could just use the formulas at the end to do that.
I got you. So when I'm initially looking at it, I'm thinking of these right here on the left, these wind turbine things. Admittance for that is, I mean, to add these up, admittance would be easier. And then when you're going over here, I just kind of realized this now about what I literally wrote down, where the main helps find admittance and the name helps find impedance, because as kind of Phoenix said, if we were finding the impedance here, right, we have basically the IM1 over our voltage source. And if it was the opposite, we'd have our VN1 over our JG, where this IM1 will become that delta 1,1 over EG. So the EGs would cancel out. So then it would just be YAB equals the delta 1,1 over delta. And the same thing here, that VN1 would equal delta 1,1 over delta times JG, where this will then become delta 1,1 over delta. Does that kind of help explain it?
Yeah, definitely.
Okay. Anybody else have any questions on that, or did I confuse anybody further? Also, I haven't even fully finished this problem. Let me do that real quick. I'm gonna just put this on down. Do that there. Okay. So as I said, we put this capacitor in there as a counteraction for the inductor. I believe that's just the best way to explain that. So based on this right here, susceptance at AB equals omega. I'll just say power factor correction. This thing, right? Yeah, that's right. So then for that power factor correction, it's just beta, not beta, susceptance over omega. Power factor correction equals the 11.76, what did I write for that? 765 times 10 to the negative third, all over 4. So the power factor correction thing for the capacitor will equal 2. I don't want that one. Let's do that one. 2.941 millifarads. That answers that problem. All right. Any other questions on this problem? I know the math isn't horrible. It's just the concept to get there. I think that's the confusing part.
The beta AB Is that just a combined impedance of the?
It's not supposed to be beta. This is the susceptance at AB. So that earlier term that we found is simply just this. That's where we got this. And that's not a U, that's a 4.
11.765
Times 10 to the negative third.
was the value of our.
That was our value of our susceptance. Susceptance.
What was the value of the inductive load we found?
21.25 henries. I know that is a large inductor. But yeah, the susceptance we found earlier was at 7.6. Let's delete that and just say this. That. All right. Any other questions with this, or I'm gonna move on if not, because we found everything. That is that. That is that, and then this. Cool. All right. That one. Any other questions? Till the next one. All right. So we have this thing. Okay, so this is an oscillator question. I feel like oscillator questions, let me zoom in a little bit so you can see more. There you go. Oscillator questions, I feel like are relatively straightforward. I'm going to explain the process and then read the problem and then go for it. So you do either main or name, right? Okay. Find determinant. I'm not going to spell determinant right. Maybe I did actually. I don't know. Or is that? Sure. So, and then you set it to 0. Set it equal to 0. Okay. Then you set all S's to be equal to J omega. This is just the process. I'm writing it out, and then we'll actually get through the math. Turn those to equal that, right? You'll have a real and an imaginary. I don't know why I capitalized that. Imaginary part, as in terms with no J, terms with J's. Set the individual parts equal to 0. Find your variables. All right, that's basically the process. I just wrote it out in words. I'll do the actual math here in a little bit. So, like I said, do with the name and name, if you know, whatever works better for the problem. Find the determinant through that name or name, and set it equal to 0. Whatever the long freaking term is, set it equal to 0. And since it is easier to put things in the Laplace domain to find its admittances and its capacitance, admittances and impedances, you would then, everywhere there's an S, put a J omega. And then when you do the rest of the math on that, you will have an imaginary and you'll have a real part. And so take the individual parts of all the things that are real, all the things that are imaginary, separate the two parts of the equation, set those equal to 0. And then usually in the real part, you'll be able to find your frequency. And in the imaginary part, you'll find whatever other factor Russell wants you to find. So that is the explanation. Now let's do some math. Okay, so let me read this. So the schematic of yet another oscillator is shown in the figure. The oscillator small signal equivalent circuit is shown in the other figure, where the hybrid pi model of the BJT has been inserted. You are asked to do the following. Derive the symbolic expression for the transconductance Gm in terms of the circuit components that will cause the circuit to oscillate. Use the expression to calculate Gm's value that starts oscillation. Derive the symbolic expression for frequency of oscillation. Use the expression and value of Gm calculated in part A to calculate the value for the frequency in hertz. So we have this thing here, but unless you want to do KVO, KCL, I don't like that. So we got this whole nice thing. It's great. It's great. So y'all think we should use name or MAME? Name? Name? Okay. So name in terms, what is it? Name requires nodes. Where do you think our nodes are? So you said right in the middle, in top left?
Yes.
I kind of agree because, I mean, if you just count this whole thing, that's what you mean? Then I agree. So I'm just going to label this one VN1 and label this one VN2. Let me put this all the way up. This one kind of sucks in terms of math. There's a lot of freaking things that don't overlap well. So we'll get through some of that. Anybody take anything on that? We're good? We're good. All right. So now we're going to start doing the name. Everybody got a photo of that? Yep. So the components that are touching our first node is our G pi plus 1 over SL3 plus S, and we have a few capacitors there, so I'm just kind of combining all of them. This touches it, that touches it, that touches it. So it's S times that plus that plus that. We agree? Capacitor mu, capacitor pi, capacitor 2 are just all added up, all multiplied by S. So I just kind of put it in one and just called it C2 plus C mu plus C pi. I don't like this too. I'm also going to move this over a little bit. All right, cool.
C2 plus, is that C mu?
Yeah, C mu. So C2 plus C mu plus C pi. Yeah, okay. All right. So the things that are, what do you call it? The components that are being shared between the two, R pi, C pi, C2. Do we agree? Do we agree? Got any other questions? Yeah, cool, cool. Anybody got any questions on that? Or are we chilling? We're chilling. Cool. All right. Then I'm going to go and do this. So this just becomes minus G pi minus S C2 plus C pi. That looks like a G. C pi. It's the same thing over here. C pi. Like I said, if you got any questions, let me know. So the things that are being touched, oh, that sounds weird. The things that are touching VN2, my bad. Is this, that, wait, did I? Oh yeah, that, okay, this is touching that VN1, we're good. That, and that. So C1, C2, C1, C2, C pi, and R pi. Or if we're in admittances, G pi. Okay, so then G pi, no, that's not supposed to be negative. That is not supposed to be negative. Plus S C1 plus C2 plus C pi. And that is all multiplied by VN1. Oh, whoa, that's weird. VN1, VN2, which is all equal to, let's see. Are there any current sources that are attached to VN1? Are there any attached to VN2? Yep. Is it negative or positive?
Positive.
I agree. 0, and that current source here is GM times V pi. GM times V pi, where V pi, that's a horrible pi. All right. V pi, which is the capacitor attached to the capacitor, and that orientation is what? Nodal voltages for V pi would be what? Do we agree?
Yeah.
I agree with him. So I'm going to write that down. So V pi equals VN1 minus VN2. So if I write that then out, we then have 0 plus 0, 0, GM, negative GM. VN1, VN2. Do we agree? We agree? Bet. All right. What? C pi.
Thank you.
No problem. Yeah, I kind of hate the fact that there's no numbers, or I shouldn't say no numbers. They're not all numbers. Okay, so then when we add those together, we how do I want to do it? I'll just do this. I want this over a little bit. This then becomes G pi plus 1 over SL3 plus S all times C2 plus C mu plus C pi. Am I still going too fast or am I chilling? Good. Okay. And then the top one stays the same. Negative G pi minus S C2 plus C pi. I just copied this exact thing. This one, however, is not the same. G pi minus GM minus S C2 plus C pi. All right. And then this one, G pi plus GM. That's a horrible GM. Plus GM plus S C1 plus C2 plus C pi. All times VN1, VN2, which equals 0, 0. All right. Now we do the fun thing. As I said, we have now done the name. Well, name or main. We've done the name. So now we got to find the determinant of this thing. Who here does it algebra? Does it using algebra when they do it on a test or homework? One guy. Okay. Who else just puts it in the calculator? All right. Can I skip it, the algebra, or do we want to do the algebra? I will skip away. There's still going to be a lot of terms because I did the algebra. But I'll just skip to where there's numbers. Y'all cool if I skip to where there's just numbers in it?
In the exam, we don't have to do it with variables. Why can't we just, after this matrix, make another matrix with all numerical values, plug that into your calculator, get a numerical answer out?
Sure.
We shouldn't ask symbolic, so I'm going to say no.
Well,
No. We need to find terms using this. Basically, it's saying find the value of GM, finding your frequency of oscillation, but it's just basically telling you using the components in the network. So, okay, I like his idea, so I'm gonna go ahead and do that real quick. Okay, well. Give me just a second. I didn't actually do that when I did it, so we'll just. G pi just becomes 1 over 1300 plus 1 over SL3, 1 over S time. Nope. Take is L3. 47 microfarads. Microfarads, not microfarads. Microhenries. The 1300? Yeah.
No.
I did. So that's why I asked. I was like, y'all sure to skip it or not? So that's why I'm skipping it. Plus 21.2. Well, I'm going to write that over a little bit. I'm not even joking. I remember when I took Circuits 2, bro, imagine this is a whiteboard. Full algebra. It was actually kind of fun, I'm not going to lie. There was a lot of screaming as well. 23 or 21.277 over S plus S all times let's see, 9. S times 1.077 times 10 to the negative 9th minus 1 over, no. Whole new thing. 1 over 1300 minus S. is. Okay, cool. That becomes 1.75 times 1.075 times 10 to the negative 9th. This then becomes negative 1 over 1300 plus. So we don't, no, not plus, sorry. We don't have ninth. That's supposed to be a 9. My bad. My B. That's also even worse. Hey, there we go. That looks like a 9, right? Hey, wait, this one probably doesn't look like a 9 either. There we go. Hey, man. It's all good. So the problem is literally asking us to find GM, meaning we don't got a value for GM. So therefore, we got to find it. So wherever there was GMs, we just keep them symbolic. Minus S times 1.075 times 10 to the negative 9th, because that's the same. And that is 1 over 1300 plus GM plus S times, what the heck is that? 1 negative 9th plus. Okay, cool. Wait, is that the? That's wrong. All right, sorry. And this is 23.075 times 10 to the negative 9th. And this is all V in 1. Let's scoot this over a little bit. Yeah. Hey, man. I've passed everything, so we're chilling there.
They probably assumed you got the right answer.
Who knows? All right. So, okay. So we have this term here that is 1 over S. Doing the algebra, that will kind of screw up everything. So instead of having the highest power be S to the second, it's S to the third. So we'll skip the algebra. Y'all just trust me. So delta equals S cubed times 23.696. That's a horrible 6. 23.696 times 10 to the negative 18th. That is correct. Plus S squared. GM times 1.077 times 10 to the negative 9th plus GM times 1.075 times 10 to the negative 9th plus, is it plus S? It is indeed plus S. Plus S times 490.957 times 10 to the negative 6th, all plus GM times 21.277 times 10 to the third plus 16.366. Okay, that's, so you'll have
The S squared, does that have both GM?
Yes, those are 2 GMs. I guess I could have added more, whatever. Yes, GM. Everything that's a letter is a GM. So as you see, we have 4 terms, we have an s cubed, s squared, s, and then terms with no s. I'm just combining that as one term. Okay, so the next step is, yes, times 10 to the negative 6th. You want me to give you all a second, write it down?
Yeah.
Got it. Sounds good. Did y'all get help? Or not get help, I'm sorry. Did y'all get much out of my first review? Like, okay, cool. 16.366.
What is that, Josh? It's so bad.
Hey, this is the condensed part. You didn't even see the algebra, bro. I'll post that one.
Why don't you ever finish like your letters?
You know what's faster? No, okay. My I don't know, 3rd grade teachers.
She needs to get fired.
She probably retired at this point, bro. All right. Okay. Cool. So the next part is, oh, by the way, this determinant is all equal to 0. If y'all don't do that, that kind of screws everything up. So set it equal to 0. So this is a determinant in terms of the S domain. Now we need to turn all the S's into J omega. Okay. So putting a J omega into the S cubed would then become, let me just do this real quick. J cubed times omega cubed will then equal negative J omega cubed. That's not supposed to be squared. That's supposed to be, oh my God. Why is this not working for me? There we go. That's that. So then J squared omega squared just becomes negative omega squared. And then, yeah. So that is what that math does. So then when you have the determinant of J omega, J omega cubed times 23.696 times 10 to the negative 18th minus omega squared all times GM 1.077 times 10 to the negative 9th plus GM 1.075 times 10 to the negative 9th. And this just becomes plus J omega 490.957 times 10 to the negative 6th plus GM times 21.277 times 10 to the 3rd plus 16.366. And that is all set equal to 0. So we change their S's to J omegas, set it equal to 0. Okay, now the next part is take the real and take the imaginary. So the way Russell has you do things, he wants you to find GM and then he wants you to find frequency of oscillation. But it's actually easier if you do the opposite because you'll have, like I said, you have a real and imaginary parts. The imaginary part has it has this, which is just omega, and this, which is just omega. And when you take the real imaginary part, you get rid of the I because you're saying it's the imaginary part. That is the imaginary part. So you basically, imaginary part just has omega in it, but the real parts have omega and GM. So you need to find omega first to find GM. Does that make sense? So I'm going to take the imaginary part first. So I am of the determinant, no, that's supposed to be an A, and that's supposed to be an A. This of J omega equals negative omega cubed 23.696 times 10 to the negative 18th plus omega 490.957 times 10 to the negative 6th. Okay, and that's all equal to 0. So I'm going to basically move this over to where omega times 490.957 times 10 to the negative 6th equals omega cubed 27. Nope, that's not supposed to be 27. That's supposed to be 23. 696 times 10 to the negative 18th. Okay. Divide this omega over there. And so we'll have 490. I'm going to put that up. Oh my gosh. 490.957 times 10 to the negative 6th equals omega squared 23.696 times 10 to the negative 18th. Divide that over. We then have 490.957 times 10 to the negative 6th all over 23.696 times 10 to the negative 18th equals omega squared. Take the square root. Omega squared 490.95. Nope. That's backwards. 957 times 10 to the negative 6th all over 23.696 times 10 to the negative 18th. Do we agree? Huh? Cool. So then, plug that in a calculator. You get an omega of 45518 times 10 to the 6th. And that's radians per second. But it didn't ask for that. It asked for frequency. So frequency equals omega over 2 pi. So just divide this by 2 pi. Frequency equals 724, bless you, 443 kilohertz. I'll take a second for y'all to write. So like I said, we took the imaginary part, set it equal to 0. We were able to find our omega. So now what we're going to do is take the real part that has omega and GM. And now that we found omega, we simply just need to find GM. Did y'all find the oscillator problems not that bad? I felt like they were just math. A lot of algebra if you do it not in your calculator. All right, moving on. Did I not do that one like an idiot? Wow, I really didn't do that one like an idiot. Okay. I didn't find GM like an idiot. So now we're doing this in real time. Okay, so that will then become the real part of delta J omega equals that one. We good? Sorry. Okay, so now the real part, we take this one, negative omega. I'm going to actually go up there. Negative omega squared times GM times 1 point. Okay, why did I do 2? This thing's 1.077 times 10 to the negative 9th plus GM 1.075 times 10 to the negative 9th. And this is all, or this is being added to by GM to 21.277 times 10 to the 3rd. It's just 3rd. It's not negative 3rd. It's just 3rd. Plus 16.366. So we found our omega, right, to be, what do you call it? Omega equals 4.5518 times 10 to the 6th. So we plug that in. And basically, I'm going to plug in this value and then distribute. Is that cool with y'all? Okay. You could. I could. Which equals negative. That's positive 6, right? Negative GM times 4.902 times 10 to the 3rd minus GM 4.893 times 10 to the negative 3rd plus GM 21.277 10 to the third plus 16.336. And that is all equal to 0. So then I am going to separate it so where one side has only GM and one side has stuff with non-GM. So this will become GM times negative. Nope, that's not negative. I basically flip these to over there. Does that make sense? I subtracted those two from both sides. No, I added both these to that both sides, and I subtracted this from both sides. I'm just explaining algebra at this point, but whatever. 4.902 times 10 to the negative third plus 4.893 times 10 to the negative third minus 21. That's a negative third. 21.277 times 10 to the third all equals 16. Okay, that's weird. 16.366. So that is GM all times. Minus.
We gotta go to sophomore, John. Appreciate the review.
No problem. The other stuff. So the other two I have is Salient and Key and a 2-port. That's the only stuff I have. It'll be on the recording. Negative 21.269 times 10 to the third equals 16.366. I'll double check something.
Just write the name.
Will do. Who has a question? What's up? Oh, wait. Wait. Give me one sec. I can't hear anything. What's up?
He just was asking about the frequency.
Okay. What's the value or what? The value of the frequency is 724.443 kilohertz.
Yeah.
That's the answer. Did that help? And that helped somebody over here too. Okay. Okay. Hey, no problem.
Josh, your handwriting is horrendous, bro.
Hey man, my B. I don't care. Bro, I said probably worse stuff than the other one. So we got that. Okay, so then, GM, that's the wrong thing. GM, doing math that I need to take up. I can. Is that good? No problemo. Problem is this. All right. Sorry, I gotta find some stuff real quick. I honestly didn't even realize that I forgot to do GM, but here we go. Huh. Well, that's fun. All right. I'm just gonna, ta-da. So this, ignore what I did. I gotta figure out what I'm doing wrong, and then I'll post that on either the Teams, the Discord, or both, or something like that. Sorry, I legitimately just didn't realize I didn't do that problem, that part of the problem. But yeah. Any other questions on this one? The process is kind of straightforward, though. Do we agree? Cool. All right. Next question is 2 ports. Okay. What is that, number 3? All right. Do you want to wait? I got 2 questions left. Do you want to do 2 ports, or do you want to do Stand on the Key first? Okay. All right. Well, we got this 2 port here. Okay. No. Okay, so the resistive network shown in figure 6.1 contains the voltage control current source. Yeah, I said that right. Okay. Calculate the elements for the open circuit impedance parameters, matrix Z open circuit. Apply these parameters to transform the network into a single source T model. Label all the components. Oh, I didn't do that either. Okay. Calculate the elements of the short circuit and admittance parameter matrix Y short circuit. Apply these parameters to transform the network into single source pi model. Label all the components of the model and their values. I did not redraw the circuit, so we're just going to do 2 ports straight up. Okay, so we have this voltage here. For most of these 2 port problems, did y'all use name for almost all of them? Yes, I know it was probably like a month back, but when I did 2 ports, it was basically all name. That's all it was.
Try to do it like that in class, but yeah, I mean, it's just a small circuit.
See, I don't like doing that, so I'm not going to do that. But cool. But yeah, so 2 ports with name. Sorry, we kind of just add an arbitrary sources, right? We have this one here, which that basically is I2. Okay. Same thing here. Basically is I1. So we have a node here, node here, node here. That's already labeled V1, so I'm just going to call that VN1. And this is already labeled V2, so I'm just going to call that VN2. And this thing in the middle, VN3. A little different than how name is normally done, but whatever. Okay, so the things that are going into VN1, G1, G2. Do we agree? Cool. Things being shared between 1 and 2, 0. That's ground. So we do that, and then things being shared between VN3 and VN1 is just G2. All right, between or VN2, everything going to VN2 is G3 and G4. Between V2 and V3 is just G3. And V thing going in, the conductances going into V in 3 is G2 plus G3. Do we agree? All right. The sources going into VN1 is just I1. Sources going to VN2, I2. And the sources for that are attached to VN3, negative GM VN1, or V1, I'm sorry, which is the same as saying VN1. Do we agree there? VN1 and V1 are the same. Okay. So then put in the values, and we get this. Well, I'm sorry. We'll do this. This then becomes 0 plus 0, 0, 0, 0, 0, 0, 0, 0, negative GM. VN1, VN2, VN3. Oh, are you kidding? The walls are that thin? Okay. And so that just being added together, G1 plus G2, 0, negative G2, 0, negative G2 plus GM, G3 plus G4, negative G3, G2 plus G3. That equals VN1, or times VN1, VN2, VN3 equals I1, I2, and 0. Putting numbers into that, this is a very, very small matrix. 3, 0, or sparse. 3, 0, -2, 0, 3, -1, 0, -1, and 3. Vn1, Vn2, Vn3, which is all equal to I1, I2, well, this is 0. Okay, so we've done this. Okay, yes. Yeah, so this is just V1, so I just named it Vn1. This is V2, so I just named it Vn2, and then Vn3 in the middle. That's all I did. So then we got this, right? So Russell, I feel like, has done a couple different ways to find the open circuit impedances matrix. So I have found the two ways that I saw through my notes and looking through everything, where Z11 equals to V1 over I1. That's not 1. Where when I2 is equal to 0, which is also the same as just simply saying delta 1 over delta. Okay. And then Z21 is the same as saying volted the V1 over I2 when I1 is equal to 0, which is also the same as saying delta 1, 2 over delta. Z 1, 2 is the same as saying, V2 over I1 when I2 is equal to 0, which is equal to delta 2, 1 over delta. And then Z22 is the V2 over I2 when I1 is equal to 0, or just saying delta 2, 2 over delta. I'm going to give you all a second to write those down. Those are just, I feel like, really helpful. Well, I mean, that's just how you solve the stuff. So we're not given any current sources, right? We just put arbitrary values there, or just a variable to represent I1 and I2. So the easier one for this one is Kramer's, my personal opinion, because we actually have numbers, and it's not too bad. So once y'all are done writing, I'll get started on Kramer's. And for this one, we'll have to actually use, like, it's a 3x3 matrix, so we'll actually have to use cofactor expansion rather than it's just the one that's left when it's a 2x2 matrix. Everybody got it written down? Okay, never mind. Oh, y'all are still writing. I did not see that. Sorry. Sorry. See you. I guess I did write this stuff really, really quick. Sorry.
I understand what you're saying. Just keeping it right.
Much appreciated. Yeah.
We're all the writing teachers in elementary school that work hardest. It's funny how I'm looking at your G's look like C's.
Hey, man. It happens. Who is still? Looks like Pablo's still writing. I bet. So, in some questions, you can use not that these, right? These ways to find those ways to find them. But I feel like for this one, it's just easier to do these because we have actual values. So, plug it into a calculator. The delta of the whole matrix is literally just 24. Okay. So for delta 1, 1, first row, first column, find the determinant of this. Okay. So for Z11, that is equal to, as I said, the determinant of this matrix here, which would be 3 times 3 minus 1 times, or minus -1 times -1. So as I said, 3 times 3 minus -1 times -1 all over 24. Z11 equals 3. 1 over 3. I'm sorry, 1 over 3. That's what it equals to. We'll do Z12. Okay. Z12, cancel out first row, second column, do the matrix from that. So it's 0 times 3 minus 0 times -1. So like I said, 0 times 3, wait, I'm sorry. This is the wrong one. This needs to be for that. Sorry, delta 21. For Z21, we use this here, which is delta 12. So the process is still correct, as in first row, second column matrix. I just said the wrong Z value. So for Z21, use delta 12 over delta, which is just 0, or cross that out, 0 times 3 minus 0 times -1. So that becomes 0 times 3 times 0, -1, all over 24, which just equals 0. We agree? Cool. Now, Z12 is the opposite. Cut out the, oh wait, here we do delta 21. So it is the second row, first column, do the determinant, 0 times 3 minus -1 times -2. Am I tripping right now? Give me one sec. I just labeled it wrong. Okay. Yeah, I just labeled it wrong.
You shouldn't get 0 for 0 times 3 minus -2 times.
For 2-1? Did I do that wrong? Because 2-1 is this. But I think. Well, no, I think I might be messing something up. Let me just double check on something. 2 ports. What problem number is this? 6.1. Okay. Yeah, I think I might have messed something up. Give me one second. My bad. I think I am doing it wrong. So the first one, what is it? The 2-1, right? That represents second row, first column, right? Second row, first column. Okay, cool. So this one, second row. Okay, I did that wrong. Second row, first column. Right? Oh yeah, yes. Okay, cool. Yes, I did that one wrong. Yes. Okay, cool. This shouldn't be 0. Delta 2-1. Got it. Okay, sorry. Wait, what? My brain is dying right now. Okay.
The way you wrote it, it was okay.
Yeah.
Because your 2-1 is equal to delta 1, 2 over delta. So that's fine. Right? If the formulas are fine, then you're fine.
Yeah, that's what I'm just double checking real quick. Yeah. Yeah. Okay. Yeah, so the delta 2-1, I'm sorry, should be that, and then it's this times -2. Which, first row, First row, second column. Wow. I'm just messing myself up right now. Okay, I think Russell wrote these backwards. I think Russell just wrote these backwards, and I'm tripping. Because we're right, or as in the first one represents the row, and the second one represents the column, right? Okay. Mm. No, these are right. These were right. These were right. Yep, I'm just messing myself up. Okay, so this one would be first. What's up?
For the formulas, I think it should be E21, it should be delta 2 1 over delta.
Okay, yeah, okay.
I want to turn on, because you're trying to find E1. Yeah, that would make sense.
As in, you're saying this one? These are flipped?
Yeah.
2, 1, 1, 2? Okay. I'm just double checking on some other stuff as well. I don't want to get that wrong, you know? Have y'all written that down before? No? Okay. I'm going to, okay. Okay. Yeah, that's what I'm trying to look for. I don't want to be wrong on that, and y'all get the wrong thing for my, on the test. Okay. No, I'm coming to the conclusion that these were right to begin with. 1, 2, 2, 1, because yeah, he has them like this to where since it's Z21, we're looking for delta 1, 2. This is what's wrong. That's what I'm looking for. No, wait, I just wrote the same thing. There we go. There we go. Okay, sorry. So since I'm looking for Z 1, 2, I want to use delta 2, 1, which is the second row, first column, 0 times 3, -1 times -2, which gives me not 0. That will then give me, I'm sorry, that will then give me 2 over 24, which equals 112. I don't know why that took me so long, but sorry. 1 over 112. Okay, cool. No, because it's an. Yeah, you're right. You're right. You're right. You're right. You're right. What am I doing wrong? Do I have my matrix wrong? No, I don't have my matrix wrong, I don't think. No. All right. Well, love this. Love this. Okay. Yeah, I'm literally looking at the thing. So, I probably need to look at that real quick.
There's one there that I'm looking at. It's page 30.
Oh.
It has all those points. At least the first part does.
What materials is that? 8. 2-port definitions. Got it. Holy crap. Page 3. I wish it was page 3. Yep. Okay, I see this. I see what you're saying here. Okay. I doubt he'll just give me what it is in Kramer's rule. Yeah, I'm looking through it real quick.
I don't think I'll give it to you in Kramer's rule, but we could probably.
No, I just realized something. This whole top part is multiplied by a negative. So this, instead of being a negative 1/2 or 1/12, it just becomes positive 1/12. So it's all multiplied by a negative. Same thing here. So this should just be negative, and that should be negative. That's what it is. That's what it is. Okay. Okay. That makes a little bit more sense. So for this one, for delta 2(1), we use the negative of the negative delta 1(2). So this becomes first row, second column, 0 times 3, 0 times -1, which is just 0. Okay, that's making more sense. Okay, 0 times 3 minus 0 times -1, which just equals 0, all over 24. Phoenix, I just realized you multiply everything by a negative for the off diagonals. So this, multiply it by a negative. This, also multiply it by a negative. Yep. I just had my cofactor expansion wrong. That's what it was. All right. This is making more sense now. And for Z22, second row, second column, second row, second column, 3 times 3, 0 times -1. 3 times 3 minus 0 times -1 over 24 gives us 9 over 24, which then gives us 3 over 8. Cool. All right. So then when you put that together, equals 1/3, 1/12, 0, 3 over 8. Okay. Now he was talking about doing the single T model. Where'd I get what from? Matrix? Yep. So over here, Z11 I found to be 1/3. Z21 found to be positive 1/2 or positive 1/12, because that's a -1 times a -2, which gives me 2, times a negative, which gives me -2, times a negative, which gives me negative or positive 2, all over 24, which simplifies to 1/12. Cool. All right. And then the same thing there, 0, 3/8. Got this. So then Y short circuit equals Z open circuit matrix inverted. Do we agree? So then just Y short circuit equals, when you plug that into a calculator, 3, I'm going to do this, 3 negative 2/3, 2/3, 0, and then 8/3. So we have that. So it asks about the T models and stuff. I kind of didn't do that, but I can draw it from materials if you want me to. So T, yes, negative 2/3 for the top right. 1, 2. Yep. Well, when doing that, literally just take this matrix, put a -1 on it, and you'll get this. Yeah. Okay, so I put it in the calculator, and I'm not even trying to do the actual math on that one. I'm just putting it in the calculator on that. The T model. You want me to draw the T model and pi model? Okay. So the T model is this. This is positive minus V1, I1, positive minus V2, I2. This polarity is like that. -1/2 I1. This is also ground. Now, I did not look at this earlier. We can try to piece it together if y'all want, or I can move on. Yeah, we don't have that much time. The Salem key's not going to take that long, but it probably 10 minutes is probably what I need. But that is the T model. I'm going to insert a page real quick, so that's going to move real quick. Okay. All right. So that's the T model, and that is 7/24 and 1/4 on the top. Do I know why? Not at the moment. And then the Y, or not Y, the hybrid pi becomes this. Right. Yeah, 1/4 and then 7/24. Do I know at the moment why? No. Because like I said, I did not draw the models and try to figure that out. How to do that? Yeah, I can do that. Yeah, I can do that. Okay, so then this, are we good drawing it, Wes? Okay, cool. And then the pi model becomes like this. All right, that's that one. Yeah, I'll get back to you on why this is the case. The two things that I'll need to get back to you on are the T and pi models and GM. I think GM should take GM for the previous problem for the oscillator. Yeah, that's fine. But I'll just do it. When's y'all's exam again? Wednesday, right? Wednesday. All right. And that is 2/3, 7/3, 2/3 times V1 and 2. I know those values. And these would be in admittances because we're looking at Y. This is associated with Y short circuit, and this is associated with Z open circuit. So these are all in admittances, and the top one is all in impedances. Does that make sense? Cool. Y'all still writing? Okay. One more to do. We got like 10 minutes, so we're chilling. No, well, we have this reserved till 3. Will there be something coming in after this? I don't know. We'll find out. Everybody good? All right. Last problem. Sailing in, or what is it? Filters. Not sailing in key, but filters. Okay, I'll just write it. The op-amp circuit shown in figure 57 is a multiple feedback active RC filter. Apply the component types and values shown in the schematic to determine the type of biquad filter function generated by this circuit and the biquad parameters K, XX, omega P, and QP. It says KXX because that K is usually a gain factor, but it's the XX instead of the XX usually there. It tells you what type of filter it is. So it could be HP for high pass, BP for band pass, or LP for low pass. So this whole problem can be found in his materials. So I'm going to switch to his materials real quick. I downloaded this. Book 2, Chapter 3 is your best friend. I forget what materials this is. I think it's either 8 or 9. So I'm going to scroll down a little bit, and I'll tell you the page that I'm going to start on here in just a sec. I think I need to keep going. Yep. Okay. So another thing that was important to note, it said, so this is page 36. Cool. It'll stay there. This says multiple feedback active RC filter. So we need to look for that in this book 2, chapter 3. Okay. So we have this. Keep going. Keep going. Keep going. Multiple feedback biquad filter is denoted as that. This is the large formula here. Okay. So if you were not, that's basically what you plug all your values in. Okay. Where you have these blocks here, which represents Y 1 through 5. Okay. So this, I would write down this thing real quick. I would write down that formula. And this is for, write that it's explicitly for multiple feedback active filters. Because I think there's another one that's in terms of impedances, and that is in the top of this book 2, chapter Z. Or chapter 3, I think it was. But that is important to have for multiple feedback active filters. So that is not how I solved this problem, because there is a shortcut based on the actual problem. I will show you here shortly. Has everybody written it down? Okay. So let me do this. Okay, we'll do that and this. Okay. So we have C1, R2, C3, C4, R5. And this is multiple feedback, right? So we need to be in impedances. I'm sorry, admittances. We need to be in admittances, okay? Well, if you scroll on down this thing, we'll have this handy table here. That tells you if something is a low pass, band pass, or high pass. So look down at what is C1, or what is the first parameter? What would be our Y1 in this thing? Boom. And then just kind of make sure everything else matches. The impedance of our second component would be 1 over R2. Third component, SC3. Fourth component, SC4. Fifth component, 1 over R5. Tells you it's a high pass filter. Simple as that. So this is the, this is the shortcut that I used. It tells me it's a high pass right away. So this K value thing, right, is going to be a K high pass, like you said. So now we keep on scrolling. This tells you the multiple feedback biquad for low pass. Keep scrolling. Band pass. That's not what we need. High pass. Okay. We'll scroll down a little bit more. We have these formulas here. Literally it. Except, well, this is for a specific case. Don't worry about this. But the equivalent coefficients is literally this. So it's that this equals C1, C4. What? Well, this one is easy. Maybe 100 on this problem. C4, omega P, equals 1 over square root of R2, R5, C3, C4, and then omega QP over QP equals C1 plus C3 plus C4, all over R5, C3, C4. Okay. The only hard part is a little bit of algebra, because as he says, we need to find KXX, which we found as a high pass, omega P, and QP. QP just will require us to do a little bit of algebra. Can I take the left half this thing off of my screen? Yeah, cool. Okay, cool. So then this, just do some algebra, and this will eventually be KP equals. Actually, let's just do this real quick. Let me do the actual algebra. I'm just going to say this is X. X times QP. QP equals omega P over X. So that just becomes omega P over C1 plus C3 plus C4, all over R5, C3, C4. Okay, so with the values that we are given, where yes, sorry, this whole thing here is just equal to X, just for the algebra, makes it simpler. So let me do this. QP equals that. Does that make sense? Okay, so with the values for C1 equaling 4.7 times 10 to the negative 9th farads, and C4 being 2.2 times 10 to the negative 9th, KHP simply equals 2.136. What are our units for K values? Technically, it's unitless, or the same as unitless is just saying volts per volt. I guess it's not unitless, but volts per volt. So that's what KHP equals. Okay. And now for omega P, our value for R2 equals 1.2 times 10 to the third ohms. Well, yeah, put F there, right? R5 equals, where's R5? 270 times 10 to the third ohms. C3 equals 2.2 times 10 to the negative 9th farads. And C4 also equals 2.2 times 10 to the negative 9th farads. So when you plug all that in, omega P equals 25.252 repeating, or I should say this 52 repeats. That all repeats. Kilorads per second. When you plug everything into this mess here. If you want to do that, go ahead and check me. Which you might need to do. And then QP, right? For define QP, we have to have omega P, which we just found. Omega P is this. C1 equals that 4.7 times 10 to the negative 9th farads. C3 equals 2.2 times 10 to the negative 9th. C4 also equals 2.2 times 10 to the negative 9th farads. And then resistor 5 equals that 270 times 10 to the negative third ohms. And when you plug all that in, QP equals 3.626. That's it. For the Salient key, or this is not a Salient key. I'm sorry, I keep saying that wrong. This is a multiple feedback active RC filter, because Salient keys are something else. Like I said, this book 2, chapter 3, amazing. So if you scroll all the way up to the top, well, okay. I will tell you, basically, and I on my test there was a problem, or I got this problem actually wrong because I was a little bit later than he started the test. I wasn't late because he started the test a little bit before the class, where there was. Let me just. I don't have that on here. Do I? No, I don't think I do. No, I don't. I don't have it on here. But basically, there was a multiple feedback RC circuit, and there were values that were the same. Like there was like a C2 and an R2. So instead of making that as one in add minutes, I thought it was a typo because there was one add minutes that was like 0, or there was a third add minutes. I think there was none of them. So I just thought it was a typo. But someone had asked that it wasn't, or someone had asked a little bit earlier if it was a typo, and they said no, so I got that one wrong. But yeah, so any full questions on everything?
Is that the same case for any major?
Yes, but the shortcut I showed you does not work for everything because, yeah, the whole table thing. If I can find it again. That's the only thing with this whole thing. You're going to be scrolling forever. Here we go. Here we go. This equation here, true for everything. This equation here is going to be true for everything. But these equations here that we found from the high pass, this was just for high pass. Just for high pass. If it wasn't, yeah.
Is there low pass and another one on there?
Yes, this is low pass right here. So you'll have those right here.
Basically, look at the table, find out which one it is, scroll to the appropriate one, write down the equations, wham, bam, done.
Yep. And I'm pretty sure on my test, instead of having to find what type of filter it was, as in low band or high, it was given. So we just look at the table. So that's why this one is pretty straightforward. The 2 ports, also not bad. That was just me with some stupid algebra mistakes. Oscillators, I also feel like aren't bad. The only ones that I think would give you the issue is the first one I did, which was the power, because that was given on our test. That one was the one given on our test. So, yeah. Anyone else got any questions? Nope. I would just take a day, figure out everything I just said, and then, yeah. Oh, shoot. Nope. No. We're going to cancel that. All right. So I'm going to stop the recording. Yep. All right. Save. Is the recording off?
Yeah, so,